All right, let's start our lecture today. Good afternoon, everybody. Yes, on Tuesday we discussed about how to solve the Newton's law problem using the point of view of free body diagram, and we also have discussed about two important kinds of resistance: the normal resistance and also the fluid resistance. And we also have discussed about the centrifugal force, okay, the inertial force that's one feels if you are an accelerating observer. Okay, now this is a slide that we arrived at last time. You can see in the point of view, if the ball is now rotating about the center, from the point of view of an observer who is attached to the ball, the observer will see that the ball is the force acting on the ball is balanced. Okay, so apart from the tension that pull the ball towards the center of the circle, there's a so-called centrifugal force. Now, the centrifugal force is not a real force. It arises only because the observer himself is accelerating. So it's a fake force, so to speak. But the effect is there. Okay, if you look at everything from the point of view of a non-inertial observer, that will be easiest way for you to describe our world is to introduce the so-called centrifugal force to explain everything that's happening here. Now, I have an interesting example of centrifugal force that you might find interesting. Let me show you a demonstration of that. Now here we have some very thin strip tied to a rod, and here the base of the strips can be varied. The distance can be varied smoothly. Now, so let's see what happens when we rotate it. When we rotate the rod, you can see the whole structure become flattened. Okay, it tends to flatten itself, and this point of at which all the strip ends is now rising. Okay, you can see more clearly when I rotate fast. When I rotate it fast, you can see many different kind of patterns were happening, but at high speed, you can see the base will rise, and then the pattern will become flattened. Now, why is it so? Because when we rotate it fast, we need a large centripetal force, right? The centripetal force is proportional to omega squared. The centripetal force is mr omega squared. So when we spin it fast, the centripetal force required is large. So what provides centripetal force? Of course, it's from the tension on the strip. Okay, the tension on the strip pull the matter towards the center, towards the axis, to provide a large centripetal force. But if the orientation of the strip in this way, then there's no horizontal component. Okay, there's no horizontal component of the strip because the strip is all vertical. So the strip itself cannot provide a horizontal component of the tension that pull the strip towards the center. So it has to be flattened. Okay, if it's flattened this way, then there is a horizontal component of the tension that can provide the centripetal force. But there's another way of looking into the matter. Instead of saying that there's a centripetal force that when it's flattened, it provides the horizontal component, we can imagine that we are looking the whole matter from the point of view of an observer who spin together with this structure. And for that observer, the observer will feel a centrifugal force. The centrifugal force will try to pull this strip apart. Okay, so that when it pulls it away from the axis, when it pulls the strip from the axis, the base will normally rise. Okay, so it becomes a structure like this. So from the 2 point of views, you can explain the same phenomena. Okay, just that when you are using the point of view of observer which spin together with this structure, then you have to introduce a centrifugal force, which is a fake force that reflects the inertia of a body. Okay, So here is the interesting thing. So let's go back to this slide here. Sorry. All right. Now, in the previous lecture, we also have mentioned that a new method used for doing numerical calculation is scaling. Okay, we introduced this method for doing numerical calculation because in most of the situation, we don't want to carry the very large and the very small number around in the calculation. That is very inconvenient. And this natural method of scaling allows us to find the typical time scale for the problem. And also from that typical time scale, we can choose a suitable delta t. So that is the idea of scaling. Okay, if we scale the problem, we scale the differential equation, it will enable us to choose a suitable delta t for the problem to do the numerical calculation. And also, there are a lot of problems which have the similar physics. For example, in the orbital motion under gravity, we have the moon moving around the Earth, the moon moving around the sun. All these problems, they share the similar properties. They share similar physical property. In fact, they are the same problem, just with different scale. The different scale come from the gravitational center. If you are talking about the Earth moving around the sun, then the gravitational center is the sun. While if you are talking about the moon moving around the Earth, then the gravitational center is Earth. But they just are the same problem. They just differ from the scale. Okay, so it may be useful for us to devise a computer scheme which enable us to solve all of this problem at once. And when we apply different scale to different individual problem, we will come up with a solution. That would be nice. So here we introduce the scaling method. Now let us move a little bit forward in our teaching. Suppose we are dealing with a problem of an apple falling towards the Earth. But the apple is initially placed at a very large distance from the Earth, which is not placed close to the surface of the Earth. It is placed at a very large distance from the center of the Earth. So at this distance, which is maybe several Earth's radius, the expression that's the weight being a constant does not hold. Near the surface of the Earth, the weight of the apple is mg, right? Where g is 9.81 meter per cent square. But now at such a large distance, we cannot apply such a relation. We cannot assume such a relation to hold. We must go back to the law of universal gravitation. Newton says that when two spherical bodies are attracting each other by the force of gravity, the force is proportional to the product of the mass of the two bodies. Now the big M is the mass of the Earth, the small m is the mass of the apple, and it's inversely proportional to the square of the distance between the center. Now R is the distance between the apple and the center of the Earth. Now we put a minus sign here because the force is attractive. Okay, and that's important in calculation because when this R is increasing, it means going outwards. So the negative sign means the force is being directed inwards towards the center of the Earth. Okay. Now, but Newton's second law, it also says that the force produced on the apple is proportional to its acceleration. So F equal to ma. So when I release the apple at this position, the apple will fall under gravity with an acceleration a, right? And that's given by Newton's second law. If we equate the force expression of gravity together with the ma, then we find that the m, the mass, they cancel on both sides of the equation. Now, this is an important, interesting relationship. M is actually referring to the gravitational mass, the mass that produces the gravity force. But the m here in Newton's second law, it actually refers to inertial mass, the mass that is reflected from the inertia of a body. But it just happened in Newtonian mechanics that the two masses are equal, and they cancel in this equation. And so the resulting acceleration will be independent of the mass of the apple. So whatever things it falls under gravity of the Earth, they just fall with the same acceleration. It's independent of their mass. So the acceleration is now being equal to minus gm over r squared. And the acceleration can be written as d squared r, the second derivative r respect to t. So here is the differential equation that we want to solve. But the differential equation is quite difficult because this can not be integrated in a straightforward manner. So we are trying to solve it numerically. Now let's see what we are going to do. Now we should choose a natural length scale of the problem. And for this problem, we are studying maybe how long the apple falls to the surface of the Earth. So the natural length scale of the problem is the radius of the Earth, which we call big R. Okay, the big R is a constant. It is just the radius of the Earth. And we also would like to choose a time scale t, which is to be determined later. Now, we don't know what this time scale t is. We just introduce it first, but we know that it's a constant. And this constant eventually will depend on the other parameter, such as big R or G and M. Let's see how we will determine the big T later. Now, after we define the length scale and the time scale, we define the dimensionless quantity. The dimensionless displaced position of the apple is defined as the small r, the actual distance, divided by the big R. So this is the distance of the apple from the Earth. X reflects the distance of the apple from the Earth. But now, X takes on a very special unit. It measures the distance with reference to the radius of the Earth. So if X is equal to 1, that means small r is equal to big R. The apple is on the surface of the Earth. If I say X is equal to 2, that means small r is equal to 2 big R. And the apple is now situated at twice the radius from the center of the Earth, twice the radius of the Earth from the Earth center. Okay, so that is what this X means. And we also can define a new time variable, which we call tau. Tau is defined as small t divided by big T. Now, you can notice that because the big R carries a dimension of length and the big T carries a dimension of time. So small r divided by big R, small t divided by big T, they are dimensionless. So they are the dimensionless variable which reflect the distance and the time in this problem. Now we would like to express the whole equation of motion in terms of these two dimensionless variable, x and tau. Now we know that the velocity of the apple at any time is given by the r dt. But in terms of x and tau, we can rewrite this equation as, because small r is big R multiplied by x, and small t is big T multiplied by tau. But big R and big T, they are constant, so they can be taken out of the integral, right? They can be taken out of the derivative. And that means the velocity in the usual form is related to the dimensionless velocity dx d tau by the simple relationship. Okay, if you take the real velocity is equal to the dimensionless velocity multiplied by the big R divided by big T. Okay, so this is the relationship between the two velocity. The one is the velocity maybe in SI unit. The other is the velocity expressed in a certain special unit. Okay, that's special dimensionless unit. Okay. Now we can also go one step further. We can express the acceleration in terms of the dimensionless quantity. Okay. The acceleration is the second derivative of r respect to t. So it becomes d dt of dr dt. As we know, dr dt is capital R over T, capital T dx d tau. And when I differentiate it further with respect to time, one more time with respect to time, then the T can be written as capital T multiplied by tau again. And the capital T can be taken out, right? Because it's a constant. Also, the big R over big T can also be taken out. And so it results in big R over capital T squared multiplied by the second derivative of x with respect to tau. Okay. And we also can modify the term on the right. It's gm over small r squared, but small r squared is big Rx. So now it becomes 1 over big R squared, gm over x squared. Now, so we put everything back to the equation. This is the the acceleration. The acceleration can be written at x and tau now. And this is the term gm over r squared. Now is written in terms of x. Now we can put all the constant together. The gm are of course constant, but in this problem, the r, the big T, they are also the constant. So we can put all the constant together in this form. So we put all of them on the right-hand side of the equation, and it becomes gm t squared over r cubed. Okay. Now remember one thing, we haven't defined what is T yet. The T seems to be arbitrary, an arbitrary constant, which carries a dimension of time, right? We haven't defined it yet, but now it's a position. It is a suitable moment for us to define it. We should define the T in a way such that this branches of quantity is becoming 1. Like this is always possible because we can choose whatever T we like. And we choose the capital T in such a way so that this whole branches of quantity is becoming 1. Okay. And if this is the case, then I can find out what is capital T. The capital T is in fact equal to capital R cubed over gm the square root. Okay. So this is our choice. If I take the big T with this form, then I would be able to make my equation very simple. I would be able to transform my equation of motion into a form that is completely independent of all those complicated constants. And this is the resulting equation of motion. Now you can see in this equation of motion, you cannot see the all the constant. You do not see big R, you do not see big T. Even the G and the M, they are eliminated. Okay, you cannot see them because they are already hidden inside X and tau. Okay, by using a suitable definition of the space scale R and the space scale and the time scale T, all the constants are hidden inside the new variable X and tau. And that exactly allows us to obtain a very simple form of the equation of motion. Okay. Now let's do the real calculation. How do you proceed with this abstract formula? Suppose the apple is now released at a distance 2r from the Earth center. R is the radius of the Earth, so that means the apple is now released as twice the radius of the Earth from the Earth center. Okay, so that means that the initial x, the initial value of x, which we call x1, is small r divided by big R, but small r is 2 big R, so it becomes 2. Okay, and since the apple is released from rest, right? We released it from rest, so the initial velocity is 0, and in terms of the dimensionless velocity, it is also 0. Because the dimensionless velocity and the velocity in the usual form, they are just related by a constant. So if one is 0, the other one is also 0, right? So I start with this 2 initial condition in our numerical calculation. Now, so what kind of time scale should we choose to do this problem? Now you can see, now in this equation, we don't have any constant. Okay, we only have x and tau. They are related to each other, not by a very big or very small number. There is no 10 to the power 7 or 10 to the power -5 factor appearing, right? So we expect everything to be changed with a time scale that is of the order of 1. Okay, so the natural time scale of this problem is 1. By 1, I don't mean exactly 1, but maybe a few. It may be a fraction of 1 or maybe a few. But it cannot be 10 to the power 6 or 10 to the power -5. It's not possible for this simple equation, right? So we expect the natural timescale of this problem to be of the order 1. Okay, and if the natural variation timescale is of the order 1, then delta tau, the individual step in doing the numerical calculation, should be much more than that. And it should be safe to choose the timescale to be 10 to the power -2. Okay, I choose the timescale, I choose the delta t, the step of the calculation, to be 10 to the power -2 or 0.01. Okay, sorry for the typo here. I should write down the tau because I'm talking about the tau here in the numerical calculation, not t. Okay, t refers to the variable in SI unit. Now I'm talking about tau. Now, so with the initial position equal to 2 and initial velocity, dimensionless velocity equal to 0, I now do the numerical calculation using delta tau equal to 0.01, and that is my result. Now, it is very clear that when tau reaches 2.57, this value I read off from the Excel table. Now, don't rely on the graph in determining this time, because it's not accurate just by looking at the graph to determine the time of impact. Okay, you have to go to the Excel table to look at the time where the x is equal to 1. That is the impact time. Okay, so at this time, 2.57, the apple will just reach the surface of the Earth and collide with the Earth's surface. Okay, and this happened with a certain velocity. I can read off the velocity from the column B here, and it turns out that the velocity, the dimensionless velocity, is -0.99. Okay, so these are the results we find. Now, how do we go back to SI unit? Because we are doing the calculation with a very special kind of unit, such that x and tau are dimensionless. Eventually, we should go back to SI unit, so we can know the true length and the true time, right? Now, if we first calculate the timescale t, we know that the radius of the Earth is about 6.37 10 to the power 6. The gravitational constant is 6.67 10 to the power -11. And the mass of the Earth is about 6 times 10 to the power 24. We plug in all this number, and we find that the time scale is about 807 seconds. Okay. Now, so how can I convert the dimensionless time back to the SI unit of time? I can just multiply the time scale t, get capital T, with the time that I find from the calculation. And after multiplying them, I got the time in SI unit. It's 2070 seconds. This is the time I got in SI unit. It means that at this time, the apple will fall to the surface of the Earth. Now, I know that the velocity in SI unit and the dimensionless velocity, they are related this way, right? And so I plug in the capital R, capital T that I just calculate, and then I plug in the dimensionless velocity that I've just found. I find that the real velocity in SI unit is 7830 meters per second. So this is the velocity of the apple when it just collides with the surface of the Earth. Now, suppose we are doing this problem not on the Earth, but on Mars. Suppose now the apple is now raised to a distance which is twice the Earth, the Mars radius from the center of Mars. So how do we do the calculation? Do we need to do it again? No, because we already have done the suitable calculation in a dimensionless form. What the difference between, the only difference between the problem that we just calculate for the Earth and for the Mars is a time scale and the length scale. Now the R and the T, the R now becomes the radius of Mars, but not the radius of Earth. And the T will change accordingly because the R change, and also the mass now is not referring to the mass of the Earth, it's referred to the mass of Mars. So we put in all the parameter for mass, the radius of Mars, the mass of Mars, and we now calculating a new time scale tau, which is different from the time scale capital T that we found previously for Earth. So with this new time scale, I can calculate the new time. Okay, the new times will be 2440 seconds. Okay, now so with scaling, we solve not only one problem, but a whole range of problems. This problem have the same physics, but just they have the different scale. Okay, so we do not need to do the numerical calculation again because that numerical calculation is universal to all this problem. We only change the scale. Okay, when we change the scale, we scale back the result to the real time and the real velocity. Okay, so that is what we have done. Do you have any problem so far on the numerical calculation? Any question about it? If not, then we should go to a new chapter on work and energy. Can you see the PowerPoint slide now? Now, first, we want to introduce to you the concept of work done. I think you learned it in high school, right? What is work done? Anybody answer me? What is work done? You can type it on the chat box. What is work done? Anybody knows? Nobody answer me? Come on, you already have learned it in high school, right? You should know it. Or at least you should have a rough concept about what it is. Yeah, energy transfer. Good answer. Work done is an energy transfer, right? How you transfer, but how you do transfer the energy? Yeah, that's a false. Yeah, that's false. So when I combine the answer from two of you, I got the whole answer. The work done is a transfer of energy by the application of a force. So that is a definition of work done. So very good. It's very good of you to answer the question. So this is the idea. The work is the energy transfer by the application of force. Now, the work is not a kind of energy. I must make it clear. The work is not a kind of energy. Do you know what I mean? Now, by the kind of energy, I mean something that a body process. For example, when a body is moving fast, it processes the kinetic energy. When a body is raised to a high altitude, it possesses a potential energy. That is the energy that's the body process. It belongs to the body. But work is the energy that is transferred from one body to another, but it's not yet the energy processed by that body. Okay, when you do work in raising a body to a high altitude, your work eventually will go to its potential energy. Okay, but the work itself is not the kind of energy that the body possesses. It is a potential energy that the body possesses. Now, there's a common analogy for that. The money in your pocket and the money in your bank account belongs to you. They are the money that you process, right? Suppose I give you $100. The $100 that I give you now at this instant is the work. It's the money transferring process that I give you. I may give you by cash, or I may give it to you by a check. You may now take my $100 and put it in your pocket. So that become a form of energy that you process. Or you may take my $100 and put it in your bank account. That is another form of energy that you may process. But at the time when I transfer this energy to you, it is not a kind of energy you process. It's just an energy transferring process. So that is a common analogy that helps us to understand the concept of work. Now, the so-called work energy theorem says that the work done on the system will change the energy of the system. Just like when I give you some money or I take away some money from you, it changed the amount, the total amount of money that you have, right? And the elementary definition of work is the dot product, F dot S, or Fs cosine theta, where the cosine theta is the angle between the force and the displacement, okay? The force dot product with the displacement. The unit of work is joule. It takes the same unit as energy because it's energy transfer. So of course it has the same unit as energy. And from this equation, you can see that the joule, the unit of energy on work, is equal to the unit of force, which is Newton, multiplied by the unit of displacement, which is meter. So 1 joule is 1 Newton meter. Now, but that definition is valid only when the force is constant. If you simply multiply the force with the displacement, that is true if the force remains a constant during the period of your application. If the force is not constant, then we cannot simply apply this formula. Now, we will discuss about the one-dimensional cases with a variable force, a force that varies when the object travels. And we will only briefly discuss about the generalization to 3 dimensions. In fact, I will not be able to discuss about this because I do not have sufficient time. I want to discuss the variable force problem in more details with you, and so you may be more have a clear idea of what this is about. Now, how to do it? How to calculate the work done by variable force? The answer is by doing an integration. Now, we consider a motion in along the x direction, which is a one-dimensional motion, and we define the motion. We divide the motion into many small steps, and I call each of these steps delta xi. The I, the subscript here, means the displacement in the I step, where the displacement is supposed to be small because we divide the motion into a lot of small steps. So we now have when the object goes from x1 to x2, it has a displacement delta x1. When it goes from x2 to x3, it has displacement delta x2. Now, we suppose each of this length interval to be very small, or the corresponding time that the object travel is very small. So that inside each of this interval, the force is essentially constant. In the first interval, the force is F1. In the second interval, the force is F2, and so on and so forth. So if the force is essentially constant, we can apply the elementary formula for the work done. We just multiply the force with the displacement. So the first interval, the work done is F1 delta x1. The second interval, the work done is F2 delta x2, and so on and so forth, until for the n step, the last step, where the work done is Fn delta xn. And when we form the sum of all this work done, we get the total work done. And that is expressed in the form of summation Fi delta xi. And suppose we are using more and more steps now. So each of the steps is becoming is tending to 0. Suppose we are using infinite number of steps, so each of the delta x will be tending to 0. And with this summation is a Riemann sum that goes to the integral of f with respect to x. And so the work done is given by the integral of f with respect to x. Okay. Now, how do we visualize the work done graphically? We can plot a graph of f versus x. Now, this is the vertical axis is the force. The horizontal axis is the displacement. So the force varies as the object travels. It varies from x like this. Okay. Now we divide it into many strips. And for each of the strips, the width, the displacement is delta x, which is sufficiently small. So the area bounded below by the curve along a strip is equal to Fi delta x, okay? Where Fi is the force at the ith interval and delta x is the displacement in the ith interval. For simplicity, we assume the delta x to be the same at every interval, so we drop the I, okay? We do not include the I here. So when the delta x becoming 0, the integral of f dot over dx from a certain starting point A to ending point B will just be equal. You can see because each of the strip containing area that is Fi delta x, when we sum up all this area, it becomes this integral, and this integral represents the area below the fx curve. So this is the graphical representation of the work done. The work done is the area bounded below by the fx curve. Okay. Now let's play around with a simple example. A spring. Okay. Now here we have a spring. Okay, a spring like this. So when we stretch a spring, it extends, right? And in many experiments, we find that the force exerted by a spring, the spring would try to pull me back, right? And in many experiments, we find that the force the spring exerts on my hand is proportional to the extension. If we stretch the spring more, the restoring force will be larger. Okay, so that's called Hooke's law. Now, Hooke's law is not a basic law of nature. It's not a fundamental principle of physics. It is just an empirical law. It is summarized from many experiments, and there's no guarantee that the spring you find in your home will obey Hooke's law. It's just a kind of approximation that applies to many springs. So if you stretch it more, it will have produced a larger force. So we can approximate the force by this equation. The force being proportional to the extension x. X is measured from the unstretched position of the spring. So when x is equal to 0, the spring is unstretched. At a certain x, the force is proportional to the extension, and the proportional constant is k. Now the k is the characteristic of a spring. If you have a tight spring, if you have a spring that is very difficult to scratch, then the force constant k will be large. Okay, so it depends on what spring you use. And the minus sign is there because the force due to the spring is in opposite direction to the displacement. So that's why there's a minus sign. Okay. Now suppose we apply external force. Now, can you distinguish the two force? The first force is a force due to the spring. When I stretch it, the force on the spring pull me back, right? And that's given by minus kx. But the external force is a force due to my hand. My hand applied an external force on the system, right? So the external force is in opposite direction to the force on the spring. And suppose they are equal in magnitude. If I pull it slowly, okay, I'm applying a force that is always equal to the force on the spring, okay, but in opposite direction. So my external force will be negative F, okay? My external force will be negative F, and that will be given by plus Kx, okay? This is my external force. Now, what I want to know is how much work that the external force does on the system. If I put it like this, how much work do I input on the system? That is the interesting thing, right? Because it's the energy that I transfer to the system. That is the thing I want to know. So what I calculate is not the work done by the force of the spring, but the work done by the external force. So I integrate the external force over the displacement from the unstretched position 0 to a certain extension x. So I now put in the external force Kx, and I do the integration. The integration is simple. Integrating x is just x squared over 2. So I now get half Kx squared. And that is the work done that my external force does on the spring. Now I can understand why there's a factor of 1/2 by considering the external force, the graph of the external force versus x. Now the external force varies with x as Kx, and that means it's a straight line, right? The straight line has a slope equal to K, okay? Now, as we say, for the graphical interpretation of work done, the area bounded below by the FT graph represents the work done. So that means this area, this green area, now represents the work done, okay? Now the final extension of the spring is X, where the final force is Kx. This is a final extension, and the final and the force on the spring of the and external force at the final position. Now, how do we calculate this area? This is a triangle. So the area is given by half the base multiplied by the height. The base is x, the height is Kx, so that we get half Kx squared. The factor of 1/2 is there because the external force is increasing linearly with the extension. So instead of getting Kx squared only, we get a factor of 1/2 due to the force increasing with the displacement. And this is exactly equal to the area bounded below by the curve. Okay. Now, before the break, let us study a slightly more difficult problem. It is about the work done on bringing an object from infinity to a certain distance from the center of the Earth. Okay. Now, suppose we have an apple again. We consider apple again. The force of gravity is pulling this apple towards the center of the Earth, right? So the big F here represents the force of gravity. It is pulling the apple towards the center of the Earth, and its magnitude is given by GMM over R squared. This is the law of universal gravitation by Newton, right? The minus sign indicates that this is towards the center. Okay. Now suppose you have a Superman, and for some reason the Superman will like to transport the apple. Now don't ask me why the Superman want to transport the apple, but somehow he wants to do it. He wants to hold the apple such that the apple will not fall due to the gravity of the Earth. So the Superman now applying an external force that balances the gravitational force. Okay, so the external force that the Superman apply is exactly equal to the gravitational force, but the opposite direction. So instead of minus sign, you now have a plus sign, and a GMM over R squared is the same. Okay, now we further suppose now the Superman brings the apple from a pond which is very far away from the Earth to a distance R from the center of the Earth. So he is now bringing the apple from very far away to a certain distance from the Earth center. And let's calculate the work done by the Superman in this process. Okay, so we're integrating the external force over dr, but from infinity, the starting point is infinity to small r. So we now plug in the external force, and the GMM are constant, so they can be taken out. So we are integrating the 1 over r squared, or r to the power minus 2. Okay, when we integrate r to the power minus 2, the standard formula tells me that the result is r to the power minus 2 plus 1 divided by minus 2 plus 1. The power increased by 1, right? And the denominator here is the power, also the power plus 1. So we get minus 1 over r. And when this 1 over r evaluate at infinity, evaluate r equal to infinity, 1 over r becomes 0. So we do not have the lower limit. The lower limit contributes 0. We only have the upper limit, which is just minus 1 over r. And so the result is minus gm over r. Okay, so this is the work done by the Superman in bringing the apple from infinity to a distant r from the Earth center. Now, why is the work negative? You can see the work is negative. Why? Because as you see, the Superman is holding the apple, preventing it from being attracted towards the Earth center, right? So the force is in the outward direction. It's towards the infinity. But now the Superman, he moves slowly the apple from infinity to the present position. So the displacement is towards the Earth center, while the force is outward, is away from the Earth center. So the displacement and the force, applied force, they are in opposite direction. And in that case, the work done is negative because F dot ds will give you a negative sign. You are not moving the body along its direction of motion, but you are moving the body, you are applying a force on the body in opposite direction to its direction of motion. So you get a negative work as a result. Okay. Now there's a word of warning before having a break. Let's have a warning note for you. Now some people or some even secondary school teacher, they may be teaching you to use the force multiplied by the displacement to find the work done. But this formula is not does not work in this situation because the force is actually varying with the distance. So you cannot simply use the force multiplied by the distance to find the work done. Now let's see why. Now the correct way to find the work done by the external force is do this integral. Now the integral we did is integrating GMM over r squared from infinity to r. If I suppose I switch the upper and the lower limit such that the limit become r to infinity. If I switch the two limits, it becoming introducing a minus sign, right? So I add a minus sign to cancel that. I switch the two limits and I introduce also a minus sign to cancel that effect. So what I'm doing here is I integrate the gravitational force itself because now we have a minus sign. So the gravitational force looks like this, minus GMM over r squared. It looks like this. I integrate from r to infinity. So what I'm calculating is the plane area. I'm integrating the gravitational force from r, the final position, to infinity. So it becomes the area bounded below by the curve, right? It becomes the plane area as indicated in this diagram. But if you use the formula that the force is multiplied by the final position, then you got the right answer, but conceptually, you are totally wrong. Because the final position is r, right, which is here. And the final force is Fr, which is here. If you use the final r, multiplied by the final force, you get the area, the rectangular area here, which is not equal to the work done by doing integral. They are completely different area. They just happen to be the same. They happen to be the same by sheer luck. Okay, you cannot expect the same thing to be happening again for other situation, because conceptually this method is totally wrong. Okay, so for variable force, don't try to simply multiply the force with the displacement or the final position to get the work done. It's totally wrong. Okay, now so let's just have a break now. We stop the recording first. All right, let's continue with our discussion. And then we come to an important topic that's called the conservative force. Now we consider two balls raised upwards under the force of gravity. Okay, suppose we apply external force, so like my hand. I'll now raise the apple. Okay, so I want to know now if I raise the apple by certain heights, okay, which I call x, what is the work done by me on the apple? And I also want to know if I now raise the apple not directly to its final destination, but I raise it upward such that it overshoots the final position, and then I go back. So in this way, what is my work done? Is the work done the same as if I raise it directly to the final position? That is the question I want to answer. And I find that, eventually I will find that the work done that I apply on the apple in raising it to the final position will be independent of the intermediate step I do. So no matter what I do, I can raise it up and down by many times, but as long as initially I start with the same position and finally I end up at the same position, I always do the same work. That is the important thing in work done against gravity. You will find that the work done against gravity is independent of the intermediate process. It depends only on the initial and final position of the object. And that exactly allows us to define a concept, a so-called potential energy. And that's why the gravity force is defined as a so-called conservative force. A conservative force can define a potential energy. Now, let's look at the exact mathematical step in my consideration. For path A, I raise the ball, I raise my apple directly to the final destination. And of course, the force of gravity is mg downwards, right? So the force that I need to apply is mg upwards, right? In the upward direction, I take it as positive. So I now integrate mg from 0 to x, and that is my work done. And of course, that becomes mgx. Okay. Now, suppose I do it in another way. I first overshoot the final position by a height y. This y is above the final position. And then I go back to the final position. Okay. So I can divide the work done into two steps. The first step, I go from 0 to x plus y. And then I go from x plus y to the final position x. So I now do two integrals, but I find that eventually the mgx plus y in the first integral cancel with the minus mgx plus y in the second integral, because one limit is in the upper limit, the other limit is in lower limit. So they differ just by minus sign. Okay, so this term cancel, and eventually I get mgx. Now you can extend the argument to any motion. I can raise it up and down by many times. But for each of this motion, you will find that the positive work and moving upward and the negative work moving downward, they cancel each other. So they do not contribute to the final work done. And you will eventually find that as long as your initial position is the same and the final position is the same, you always got the same work done. And that means the work done is path independent. It does not depend on the intermediate process of moving the apple. It just depends on the initial position and the final position. So the technical term for saying that is that the work done is independent on path. It does not depend on the intermediate process when, how you move the apple. We might be moving it in a very complicated way, but still you got the same work done as long as the final position is the same. Okay. Now, but you may be tempted to conclude that this is generally true, but this is not so. For the work done against some forces, you find that the work done is not path independent. For example, friction. Now, friction is a kind of dissipative force. It dissipates the energy. It changes the energy into heat, right? That is you learn in high school. For this kind of dissipative force, you find that the work done is position dependent. Now, how do we say that? Suppose we try to move an apple along a table. Okay, I move this apple along a table. I can move it directly to the final destination, which are supposed to be here. So I do work against friction because friction is opposing my push. So I do work against friction. I input energy, and eventually the energy goes to heat, right? I calculate the work done in moving the apple from here to here. That is one path. But I can also move the apple to a position that is farther away from the final position first, and then I move it back to the final position. Now, the initial position and the final position, they are the same, but I move it differently. The intermediate processes are different. And eventually, I find that for friction, the two work done are not equal. And that means by the frictional force has a work done that is dependent on path. Okay, so I now go with the mathematics. The mathematics is like this. Suppose now I move it directly to the final position. And so I do work against friction. My applied force is also equal to the friction. And the distance move is x. So it's small f x. And if you like, you can write in terms of the kinetic friction coefficient and the normal reaction force. So small f is mu mg, where mu k is the kinetic friction coefficient, right? Now, but I can also move the apple like what I did previously, that I overshoot the final position. So the first work done, I move the apple from here by a distance x plus y. So the total work done is the frictional force multiplied by x plus y. The work done is positive because it's the work input by the external force. Now I move back, okay? But the frictional force has a property. The frictional force always opposes the sliding motion. So it always opposes the external force. So in order for me to overcome it, I always have to do a positive work against it. Okay, even if I move back, I still have to apply external force to oppose the friction. And in doing so, I does a positive work to it. Okay, so the additional work that I does along the second path will be Fy. So the total work done for the two paths added together will be mu k mg x plus 2y, which is of course different from just mu mg x. So the work done along path A is not equal to the work done along path B. So that means the work done by friction or the work done by external force just overcoming friction is dependent on path. It is path dependent. Okay. Now the friction, the viscous force or the drag force, the air resistance, the viscous force, etc., they always are opposite direction to the velocity. So whenever I move forward, those resistive force always act backwards. Okay, so if you apply external force that is in the direction of the velocity, for example, you move the apple along the table, the external force you apply, if it is parallel to the velocity direction, then the frictional force will always be opposing you. Okay, the external force does positive work because it's the same direction at the velocity. So F external dot V will be positive. But the frictional force does negative work because the frictional force is opposite to F and opposite to V. We can say that the external force does work against friction. Now, this is a typical term we use to describe the work done by external force. If it is a frictional force that opposes it, then the external force does a positive work against the friction. Okay, against the friction. That is what we commonly say when we refer to the work done by the external force. Okay. Now here comes the important definition. What is a conservative force? A conservative force, a force is said to be conservative. Is the work done by it or the work done by an external force just overcoming it? Now, in our previous discussion, we always refer to the external force work done, right? But the external force just differ by the original force, just by a minus sign. Okay, they are essentially the same thing, right? So the work done by external force, work done by the force itself, or the work done by external force just overcoming it. If the work done is independent on path, then we say that the force is conservative. Okay, so in this sense, in the two examples that we discussed, the gravity force is conservative because no matter how we move it, as long as the position, initial and final position is same, the work done is the same. But the frictional force is not conservative. If we slide the apple back and forth many times, if we rub it like that, right, many times, then we dissipate more energy. The external force has to do more work, right? So obviously it is not conservative. Okay, so that means the frictional force is not conservative, but the gravity force is conservative. So in general, the gravity force, the electrostatic force, etc., they are conservative force, but the frictional force and all kind of resistive force, they are not conservative. Okay. Now, I only discussed one dimension example, but in fact, you can generalize the picture to 3 dimensions. The definition of conservative force in 3 dimensions is like this. If the external force, just overcoming the force, move the body from point P to point Q along 2 different paths, the work done I got is WA and WB. If these 2 paths are arbitrarily chosen, and it happens that WA is always equal to WB, then I say the force is conservative. Okay. Now, of course, if you calculate the work done in higher dimension instead of along a line, then you need this a mathematical tool, so-called line integral. Because at each point along the path, the force direction and the displacement direction, they may change. And so the integral is not a simple integral f over x, but the integral of the force, the dot product between the force and the displacement ds. And this is the so-called line integral. But I'm not going to teach you line integral in this course. I leave it to leave the difficult things to the senior level course anyway. Okay, but you know the idea. If the work done on 2 arbitrary paths that connect the 2 points are being the same, then the force has to be conservative. Okay. Now, what is so good about the conservative force? The thing is, if I have a conservative force, I can define the potential energy. Why? To define the potential energy, I need a conservative force. And I also need an external force just overcome the conservative force, so that the external force is equal in magnitude to the conservative force, but with a minus sign. The minus sign means the 2 forces are opposite each other. And what I consider is the following. The potential energy of a certain object under a conservative force is defined by the external force in moving the object from a certain reference position O to the final position X. It is defined as the potential energy of the body at X. Now, the reference position is chosen arbitrarily. You can choose whatever position you like as a starting point. But the important thing is the work done by the external force in moving the object to the final position X is defined as the potential energy at that final position. Okay. Now, so in terms of mathematics, we integrate the external force from O, the reference position, to the final position X. And if we like, we can express the whole thing in terms of the conservative force itself. The conservative force just differs from the external force by a minus sign. So you can work with the conservative force itself, but you integrate it from 0 to O to X with a minus sign. Okay. Now, by definition, you can see that the potential energy at the reference position is 0, because if the final position is just the initial reference position, then if X is equal to O, you integrate from O to O, which is of course 0. You do not move the object. So you have 0 done. So the potential energy at the reference position is 0. And you are free to choose whatever potential reference position O you like. It is the things that you can choose yourself. It is not the kind of, it's not involved in the physics of the problem. It is just a convention that you can choose arbitrarily for your convenience. And I will show you that changing the reference position from one position to another, it just amounts to adding a constant to the integration. Now, this formula is abstract, right? Why is that work done by the external force being equal to some potential energy? What that mean? What that mean by doing integral equal to the U? What is that? Let's go back to the real thing. Now I now have a spring tied to an apple. Okay. Now I apply external force to pull the apple. Okay. So the external force does work. It pulls the spring, right? It stretches the spring. So that the work done by the external force will eventually go to what? It will store up as a potential energy, because when the spring stretch, it store up some energy as potential energy. So that means the work done by the external force in pulling the spring eventually goes to the potential energy of the stretched spring. And as we calculate, the potential energy of the stretched spring is half kx squared. Okay. So that is an example. The external force does work, and it transfers the energy to the system. Okay. So the spring becomes stretched, and there's an energy stored inside. That energy can be released. If you stop pulling it, if you release your hand, the spring will pull the apple back, right? So the stored energy will become a kinetic energy. Okay, so that is the idea. So that and that's the meaning of this equation. Now I would like to show you that the difference in potential energy between 2 points is independent on the reference position. Suppose I calculate UP minus UQ, where P and Q are two different positions. So by our definition, I integrate the conservative force from O to P with a minus sign, and to get UP, and I integrate from O to Q with a minus sign to as UQ, and I find a difference between the two, right? Now here I take out a minus sign. So the first integral will be integrating from O to Q. The second integral will be integrated from O to P, and we are going to find the difference. But I can do this trick. I know that this integral, if I invert the two limits, it becomes plus QO. Okay. So combining with the first integral equation like this, I integrate from Q to O, and then I integrate from O to P. So remember the area add together, right? If I integrate from Q to O, I calculate the area between Q and O, and then integrate from O to P, I calculate the other area. So when the two areas combine, it becomes an integration from Q to P, because the area simply add up. And the intermediate point will disappear. And eventually what I got from this formula is integrating from Q to P f dx, which is this formula. Now you see the reference position disappear. So the value of the potential energy depends on the choice of reference, the reference position O. Okay, if you choose a different reference position, you get a different value for the potential energy. But if you are interested in the potential energy difference between 2 points, that is independent on the reference position. And I will let you see that it is a potential energy difference that matter. It is not the absolute value of the potential energy. It is a difference in potential energy between 2 points that matters. Now, why? Suppose I want to calculate the potential energy gain by raising an object from the table to a height, small h, above the table. Now, if I use the surface of the table as a reference position, which I call O, then initially the potential energy is of course 0. This is my UQ. And after I raise the apple, because it now has the height h above the reference position, so its potential energy is mgh. And the change in potential energy is mgh minus 0. And of course, that's mgh, right? Now, suppose I now study the same problem, but I take the reference position not on the surface of the table, but on the ground. I suppose this level is a 0 level of the potential energy, the ground level. So initially, if the table surface is capital H, a height of capital H above the ground, initially the block does have an energy of mg by h. But after I raise it, it now measures the height of big H plus small h above the ground. So its potential energy mg by h plus small h. But if I find the difference between the two, I can see the big H will cancel. And I also get the same value of mg small h. So the meaning of this formula is like this. No matter where I choose the reference position, the potential energy difference between two fixed points, P and Q, is always the same and independent on what position of reference that I choose. Okay, so this is independent of O. Now, why is this independency so important? The reason is, I tell you a joke, okay? This is a joke only. Everybody knows that the electric potential of the main supply, the powers of the electricity supply that you access in home is in Hong Kong is 220 volts, right? So if you say the potential of your body is 0 volt, and the potential of the main supply is 220 volts, then you put your finger to the main supply, then you get an electric shock, because there is a potential difference between the main supplies and your body, and that potential difference is 220 volts. And this is that exactly is the potential difference that drives the electric field, that produces the electric field, and that drives the current through your body. So you get hurt. Okay. Now, but if you choose to say, that's a joke. If you choose to say that you use another reference for the potential energy, you call yourself, your own body, to be at a potential of 20,000 volts. You can do that. You just choose the different reference. But that makes no difference, because if you call yourself to have a potential of 20,000 volts, then the main supply will have a potential of 20,220 volts. So the potential difference is same. The same electric field go through your body, the same current go through your body, and you are going to die. Okay, so that is the important thing. It is the potential energy body potential difference that determine the force, and that determine what actually happened in the real world. It is not the absolute value of the potential matter. Okay. Now let us go back to the spring. A spring has a conservative force, and that is given by minus kx. And now we want to calculate the potential energy that the spring gain if I stretch the spring by an external force. Okay, so now I use the standard formula. The standard formula say I can work with the conservative force itself, but with a minus sign. Now, beware of the minus sign. The minus sign carries a meaning. The minus sign is there if I work with the external, if I work with the original force, because I actually is referring to the work done by the external force. So don't forget the minus sign. Okay. So with this minus sign, I will be integrating the original conservative force, but now with a minus sign. So the two minus sign will cancel. So I'm integrating with a plus sign of kx. So I now get half k squared as before. Okay, so the potential energy gain will be equal to half k squared because the work done goes to the potential energy. Now, so if I plot the u against x, I get such a curve. This is a quadratic curve. The energy increases with not with x, but with x squared. So if I double the, say I double the extension, the energy will be 4 times as large. Okay, it does not go with x, but goes with x squared. Okay. Now we work on the unstretched position of the spring as a reference position. You may choose other reference position, but in doing that, you will have an additional constant term here. Okay, but if you calculate the potential energy difference between 2 points, you always get the same answer. Okay. Now, usually we would like to choose a reference position to get rid of the constant term. If we choose to integrate from 0, the point of 0 extension, we don't have a constant additional term here. So that is more convenient to us. So that's why we usually choose that as our reference position. Now we come to the case of gravity. We raise the object by a vertical height x near the surface of the Earth. The gravitational force is minus mg, is downwards. So the formula tells me that I should integrate the force, gravitational force F, but with a minus sign from 0 to x. So it now becomes plus mg, integrating from 0 to x. So that becomes mgx. And of course, that is the usual formula that you learned in high school, right? So if you plot u against x, you got a straight line. And the slope of the straight line is mg. Okay. Now this is a slightly more complicated situation. We start with the gravity force at a large distance from the Earth. And Newton tells us that the gravity force is minus gmf over r squared. So we stick to the formula again. It says that we take the conservative force itself, but integrate from the reference position to the final destination. In this situation, it is more convenient to choose the infinity, as a reference position. So when the apple is infinitely away from the Earth, it is not affected by the Earth gravity, and it's more suitable for us to choose that point to be of 0 potential energy. So when the two bodies are getting are widely separate from each other, they do not interact, we say that the apple has 0 potential energy. That seems to be appropriate, right? That seems to be the natural choice. So, so I integrate from infinity, which is the reference position, to the final position of the apple. which is distance r from the center of the Earth. So the potential energy I get is the potential energy at the distance r from the center of the Earth. And don't forget the minus sign here, because the minus sign here will cancel with this minus sign, and I got the plus sign. And I do the integration, I get the same work done as before, and that's minus GMM over R. Now notice that for this situation, the potential energy is negative. And that means when the apple is being moved from infinity to the current situation, to the current position, energy is taken away from the apple. I do a negative work. So the energy does decrease instead of increase. And this is the potential energy curve. If I plot U against R, it goes at 1 over R. So when R tends to 0, it goes to very large value. And when R tends to infinity, it goes to 0. But the whole thing is negative. So it becomes an inverted curve like this. Okay. Now then, we shall derive the force from the potential energy. Now we only have finished half of the problem. Why? Because we are talking about the relationship between the potential energy and the force, right? And we define the potential energy by the work done. The work done is the integral of the force. So this formula allows us to go from the force to the potential energy. Okay, if we know the conservative force, we can calculate its potential energy by doing an integration. Okay, is that clear? Now we sit for a formula that goes back. If we know the potential energy, how do we calculate the force? That is a reverse problem. Suppose we know by some theory that the potential energy of a system is like this. Then how do we calculate the force acting on the object at that particular position? Now let's do it with mathematics. And we find that the result just arrived by using the fundamental theorem of calculus. Now this is our definition for the potential energy. U depends on the conservative force by the integral, integrating from reference position to the final destination, but with a minus sign. Okay. Now let us differentiate the equation with respect to x. Now you notice that the derivative x actually acts on the upper limit. Okay, the x inside the integral is just a dummy variable. After you do the integral, the dummy variable gone, and everything will be evaluated at the upper limit and the lower limit. So the functional dependence of the integral hinge on the upper limit. It does not depend on the dummy variable inside. So when we take the derivative of the integral, what we are saying is that we're differentiating the function with respect to its variable, which is the upper limit. And so the fundamental theorem of calculus, it tells us that when we do so, it will return you with the function itself. The differentiation will cancel the integration. And eventually you will find the function f evaluated at the position x, which is the upper limit. So now we obtain a formula. If we know the potential function u, we can take a derivative of the function with respect to x. And after adding a minus sign, we will get the conservative force F. This is how we derive the conservative force from the potential energy. Now, an interesting feature is the following. Suppose U is increasing with X. Now, let us plot a graph. Suppose I plot a graph of U versus X, and I find that U is increasing with X. So U is increasing when I go to a larger X. The derivative, what is the derivative? The derivative is just what? It's just a slope to the curve, right? The slope of the tangent to the curve. If I take the derivative, I will find a positive derivative. du dt dx will be positive, right? But there's a minus sign here. The minus signs tell me that if du dx is positive, then minus du dx will be negative. And that means the force will be pointing in the negative x direction because it's negative, right? On the other hand, if I have a potential energy that decreases with x like this, then I take the derivative, it will be the slope of the tangent. The derivative will be negative because the slope is going down, right? But there's a minus sign before the du dx to find the force. So the force will become what? Will become positive. And the force will become positive. It's going in the positive direction. Okay. Now, so when you see these two situations, when you look at these two situations, you can know a special relationship between the force and u. The force is always pointing in the direction of decreasing potential energy. If the potential is going up, the force is pointing to the negative side. If the potential is going down, the force is pointing to the positive side. It always points, tends to move the object to a position of lower potential energy, so to speak. Okay, so you can imagine in your mind, you can imagine now you have a hill, you have a slope, okay, and you take a marble, you place it on the slope. The marble will experience a force that tends to make it roll down along the slope. So the conservative force that results from the potential energy will always tend to make the ball roll downwards along the slope of u. Okay, so it's pointing towards the position of lower potential energy. It's very apparent if you use a bowl. At dinner, just take a bowl, the bowl that you hold the rice. Okay, if you displace the small marble, if you place a small marble to the side of the bowl and release it, it rolls down to what? It rolls down to the minimum position, to the base of the bowl. Okay, and that's exactly this picture. Okay. Now let's look at the example that we have discussed. Now for the spring, for the potential energy of the spring, the potential energy goes at half k squared. So if I take the derivative, du dx, I calculate the slope of the tangent, it becomes kx, right? After adding a minus sign, I get a force, and the force is equal to minus kx. And that means the object is being pulled back because I stretch the spring. So the object is being pulled back by the force of the spring. So the force of the spring is pulling the object back, is pointing in the negative x direction. And how about gravity? The gravity potential energy is mgx, right? If I take the derivative, is mg, and with a minus sign, I got a conservative force, which is mg, but in the downward direction. So that means when I'm raising the apple, increasing potential energy, the force will always be pointing towards the position of lower potential energy. It will always tend to move the apple back to its lower potential energy position. Is that clear? Now, how about the gravity force at a large distance from the Earth? For a large distance, we cannot rely on mgx because it's not correct. You have to use the potential energy that we calculate, minus GMM over R. When we take the derivative, the differentiation of 1 over R is minus 1 over R squared. And that minus sign will cancel with the minus sign in front. And that leaves us with GMM over R squared with a plus sign. Okay. But I know that the conservative force is minus du dr, right? So it becomes minus GMM over R squared. okay? And the slope is positive because of the derivative, but with that minus sign, the force becomes negative. So the force is pointing towards the center of the gravity, the gravity center, okay? So it's so if it's an apple, then the gravity force is always pulling it towards the center of the Earth, okay? So remember this formula. The conservative force is being equal to minus the spatial derivative of the potential energy. And it's always in the direction of decreasing potential energy, okay? Now, I better leave the next slide to the next lecture because it takes some time to explain it. I would better stop here because we have such a long lecture now in the late afternoon, and it may take me 5 or 10 minutes to explain this. So we better stop it here. Okay, so if you have any questions, then you just raise your hand. You just unmute yourself, or you can type it on the chat box. Okay, I'm now going to stop the recording.